Let's give an AI system a prompt. A red fox reading a newspaper inside a rainy London cafe. A few seconds later, the image appears. The speed of this process creates an immediate illusion of retrieval. But the system did not search a hidden server or pull a photograph from its training data, nor did it run a search for individual elements, a cafe background, a newspaper, a fox, and stitch them together into a digital collage. To understand what generation actually means, we have to stop thinking of the AI as a digital artist painting a scene and look at it as a learned probability system. The pixels on the screen have never existed in this exact arrangement before. They were computed from scratch, using purely mathematical rules. Generation is not an act of archiving or painting. It is an act of statistical computation. This equation is the mathematical foundation of modern text-to-image models. It represents the system's objective, learning a conditional probability distribution over images. You can read this as the probability of different images existing, given a specific text description. Calculating a neat list of every possible pixel combination is impossible. The landscape of possible images is astronomically large. So the neural network learns a practical approximation. Here, X represents the image, and C is the text condition. The crucial element is theta. Theta represents the learned parameters of the model, the billions of weights that approximate that vast distribution of visual data. When you type a prompt, you alter this probability landscape, shifting the system's focus toward regions containing the statistical patterns associated with your text. To generate an image is simply to sample one possible output from this parameterized, learned distribution. Mapping this probability distribution directly across millions of high-resolution pixels during training is computationally expensive. The solution is compression. During training, a high-resolution photograph passes through an encoder, outputting a smaller, dense grid known as a latent representation. This latent space retains the important structural and semantic data of the image while discarding the costly pixel-level details. Once compressed, forward diffusion executes. Gaussian noise is incrementally added to the latent representation at a random time step. This corrupted grid and the time step value feed into a central network architecture, like a UNet or diffusion transformer. Here is the core training loop. The network evaluates the static and attempts to predict the exact amount of noise that was just added. Its prediction is compared against the actual added noise. The difference between the two becomes the training loss, and the network uses gradient-based optimization to slightly adjust its internal parameters, that theta we saw earlier. The model is never explicitly taught that foxes have 4 legs or that cafes contain tables. It learns statistical regularities about geometry and lighting because adjusting its parameters minimizes its noise prediction errors across millions of training images. Generating specific content requires human language, which means the text prompt must also be translated into a mathematical format to interact with the image data. A text encoder processes the prompt, converting words into text embeddings, multidimensional vector arrays that represent semantic relationships in a numerical space. The word fox is not stored as a dictionary definition. Its embedding connects to learned relationships like fur, forests, and postures. To bind text vectors to visual features, latent diffusion relies on cross-attention, routing information from text tokens directly into the diffusion backbone. It is highly selective. The embedding for red illuminates, sending signals only to fox-related latent features, bypassing the newspaper. These are not independent database queries. They are interacting numerical constraints that are constantly updated and refined across the network's layers. Relational words like inside or reading constrain the spatial geometry between the latent features, forcing the network to mathematically position the fox in the environment. Cross-attention is how human intent shapes the probability landscape. It provides the strict boundaries dictating exactly what visual structures the network is allowed to form. When you press Generate, the system shifts to inference mode. There is no original photograph of a fox to corrupt and reconstruct. The process starts entirely with a chaotic field of randomly sampled noise, which is completely dictated by an initial random seed. The system executes the reverse of its training loop. It feeds the noisy latent, the prompt embeddings, and the time step into the network to produce a denoising prediction. Using score matching, the model calculates the direction in which probability density increases. It estimates how to subtract noise to move the latent data toward a slightly more plausible state. The model doesn't know the final image initially. Generation is an iterative cycle of numerical corrections. To balance prompt adherence with visual diversity, it uses classifier-free guidance. Increasing this tightens the trajectory closer to the text vector's constraints. After repeating this denoising cycle across dozens of steps, the fully resolved latent representation passes through a decoder, translating the compressed data back into visible, high-resolution pixels. What we perceive as generation is actually a mathematically rigorous denoising trajectory, iteratively carving a specific image out of pure mathematical uncertainty. When we look closely at the final generated image, the mechanics of the statistical process become obvious. The lighting and fur look cinematic, but the text on the newspaper is complete gibberish, and the paw's anatomy is physically impossible. These failures happen because the model optimizes purely for statistical plausibility. It predicts what pixel configuration is mathematically appropriate under its learned objective. It does not check for symbolic or physical truth. The system lacks an internal physical simulator. It has no rule engine to verify object counts and no verified model of real-world physics or language syntax. High visual quality does not equal cognitive understanding. The model captures the statistical distribution of visual features, not the physical laws governing them. This brings us to a crucial nuance regarding how these systems relate to their training data. While models are not databases searching for stock photos, they can sometimes reproduce training images. This scatterplot charts generalization against memorization. Research shows that when specific images or captions are duplicated or overexposed during training, the network memorizes those exact pixel patterns. A cluster of extracted training data sits far outside the bounds of the model's standard output. Generalization and memorization are not strictly separated. They exist on a spectrum defined by the model's training dynamics. Generation, then, is neither simple retrieval nor creation from nothing. It is the recombination and transformation of learned statistical structures, and that recombination happens inside a high-dimensional numerical space, not through a visible cut-and-paste collage operation. Generative AI is learned probability made visible. It is the act of sampling billions of numerical relationships, constraining them with human language, and decoding them from raw noise into a finished picture.